thing I'm going to do is go over factors that affect the rate of dissolution. So an example I might ask you is if you've ever tried to dissolve sugar in iced tea or iced coffee versus hot tea or hot coffee. You should notice that temperature definitely has something to do with how quickly a solute dissolves. Now, some of this, based on your previous studies, should be kind of logical, since we know after studying the gas laws what temperature has an effect on particles. But the other question is how other factors might affect how quickly a solute dissolves. So I think there's 4 or 5, maybe 3. I don't know. Anyway, we're going to go through the factors. So number 1 is increasing the surface area of the solute. Now, I mentioned yesterday that dissolution, or the process of dissolving, starts at the surface of the solute. So if you increase surface area, you're going to increase the amount of surface that is available to exposure with the solvent. So for example, dissolving crystallized sugar instead of sugar cubes. Okay, you can do, if you want, an experiment, or if you just kind of know intuitively or based on previous experiments or experience, not experiments, or experiments, maybe you did already. If you compare, say, like 5 grams of sugar cubes versus 5 grams of just crystallized sugar, and you see how long it takes them to dissolve. It's going to take the sugar cubes much longer to dissolve because they have a lower or less surface area. Another way to increase the speed of dissolution is agitating the solution or stirring it. Again, because dissolution occurs at the point where you have the surface of the solute exposed to the solvent. So if you dump a whole bunch of sugar in a glass of water and you just let it sit there, it is going to dissolve more slowly than if you actually stir it, because by stirring it, you're actually exposing more solute to the solvent, and you're going to have a higher rate of dissolving. So again, stirring brings fresh solvent into contact with the solute surface. And so basically the contact between the solute and the solvent is increased, and that means that dissolving will occur quicker. And of course, heating, as I mentioned in the beginning, temperature has a huge effect on the rate of dissolution, because what happens when we increase temperature, we increase the kinetic energy of the molecules. And so that means that the collisions between the solvent and the solute molecules are more frequent, which helps to separate the solute molecules and spread them out. So I guess it wasn't 4 or 5, it's 3 factors. So increasing surface area, stirring, and heating all increase the rate of dissolution. Now, going back to the sugar and tea example, if you like your tea extremely sweet and you keep adding more and more sugar, eventually there will be a point, based on the volume of tea that you've made, that you will be able to no longer dissolve any more sugar than what is already dissolved in your tea. For every combination of solvent with solute at a given temperature, there is a limit to the amount of solute that can be dissolved. Again, at a given temperature, because changing the temperature is going to change how easily something can dissolve. When the sugar is first dropped into water, the sugar molecules leave the solid surface and move about at random in the solvent. Some of the dissolved molecules may collide with the crystal and stay there. As more solid dissolves and the concentration of dissolved molecules increases, these collisions happen more often. Eventually, you reach an equilibrium where molecules are returning to the crystal at the same rate that they're going into solution. So this is a dynamic equilibrium, meaning that it can change, that is established between two opposite processes. Those are dissolution and crystallization. This state is called solution equilibrium. It is a physical state because we're not changing the identity of the solute or solvent. The physical state in which the opposing processes of dissolution and crystallization of a solute occur at equal rates. So now we distinguish between a saturated and an unsaturated solution. A saturated solution contains the maximum amount of dissolved solute. This is going to be specific for a few things. Number one, the nature of the solute and solvent. So it depends on what you are dissolving in what medium. It's going to depend on temperature. It's going to depend on volume of solvent. So for example, if I have 100 milliliters of water versus 1 liter of water, I'm going to be able to add more solute to the 1 liter than I can to the 100 milliliters. So how do you know if your solution is actually saturated? Well, if you add more solute, it's going to fall to the bottom, and no matter how long you stir it, it's not going to dissolve. This means that equilibrium has already been established and it is a saturated solution. If you remember from last year in biology, I talked about saturated when I mentioned saturated fatty acids. And saturated fatty acids are the ones that contain only single bonds. Therefore, every single carbon atom is bonded to 4 atoms, which is the maximum number of atoms that carbon can be bonded to. They form nice straight chains, which is why they are solid at room temperature. So the word saturated means the same thing here. It basically is implying that it is full. Now, one of the factors that I said that saturation depends on is the volume of solvent. So if we add, I'm not sure why we changed from sugar to salt all of a sudden, but never mind. If you add more water to a saturated solution of sodium chloride, of course you can add more solute. So at 20 degrees Celsius, exactly 35.9 grams of sodium chloride is the maximum that will dissolve in 100 grams of water. Okay, so we have a specific temperature, we have a named solute, a specific amount, in this case it's mass, although it's the same as 100 milliliters because the density of water is 1 gram per milliliter, and we've identified our solvent. So these are the specific conditions under which we define what is called solubility. So if we have an unsaturated solution, that is going to contain less solute than a saturated solution under the same conditions. So if at 20 degrees Celsius and 100 grams of water, you add 35.8 grams of sodium chloride, that is an unsaturated solution. So it's not full. Now, sometimes we can actually supersaturate a solution. So one way that we do that is by manipulating the solution using temperature. So if we increase the temperature, we're going to increase the solubility of the solute because the particles are moving faster, so you can dissolve more solute. So if we take a saturated solution and we heat it up so that solubility increases, and we add more solute to that solution and we let it cool, most of the time the excess that was added is going to come out of solution because the solubility, of course, depends on temperature. So for example, if I use the salt as an example, so we're at 20 degrees Celsius, we have 100 milliliters of water, and I'm going to add 38.9? Yeah, 38.9 grams of sodium chloride. Then I'm going to heat that up to, let's say, 30 degrees Celsius. We still have 100 milliliters of water. But now, because the temperature has increased, I can add more salt. So let's say I add an additional 1 gram of salt. If I cool that back down to 20 degrees Celsius, usually what happens is that you'll see on the bottom that extra gram of salt is going to settle out because the solubility at 30 degrees is more than it is at 20 degrees. Okay, hopefully that makes sense. So at higher temperatures, you can add extra, but at lower temperatures, that extra is going to come out. However, sometimes for certain solutes under certain conditions, if you leave the solution to cool, the excess solute doesn't actually come out. If that occurs, you have created what's called a supersaturated solution. This contains more dissolved solute than a saturated solution contains under the same conditions. The only way to create a saturated solution, is using heat. Okay, so a very common experiment that is done is using sodium acetate. Obviously, we can't do labs because we're all separated at home. But it is, if you want to look it up, it's something called hot ice. And there have been plenty of home experiments, and I've tried it, I think 3 times. It's never worked for me, where you mix, what was it? It was vinegar. Yeah. If you want to try it, vinegar and baking soda. Yeah. So vinegar and baking soda, the combination that normally like you use as little kids when you make your homemade volcanoes, and it creates a lot of gas. So one of the things it's going to create is carbon dioxide. That's the gas that comes out, but it's also going to create sodium acetate, which you see here. And sodium acetate is one of the solutes which is able to create a supersaturated solution. And what happens is when you have the supersaturated solution and you do what's called seeding. So let's say this is your supersaturated solution. I'll just call it SSS, supersaturated solution. And then you take one little crystal of sodium acetate and you drop it in there. It actually creates a chain reaction where the whole thing solidifies. If I've got time at the end of this lesson, I'll show you, or you can just look it up. It's called hot ice. So a supersaturated solution can remain unchanged over a long period of time as long as it's not disturbed. So again, if a crystal begins to form, that's going to continue until equilibrium is recreated at the lower temperature. So here we've got an unsaturated solution. This is at 25 degrees. We've reached dynamic equilibrium between dissolution and crystallization. We have a saturated solution. Then we're going to increase the temperature to 50 degrees. And we've gone from 91 grams. We have 9 grams of solute sitting on the bottom, which means for this volume of solvent, the maximum amount of solute allowed is 91 grams. When we heat it up to 50 degrees, all 100 grams is dissolved. That's still unsaturated. But when we cool it back down to 25 degrees, all 100 grams is still dissolved. This is a supersaturated solution because it's the same conditions as up here, only now all 100 grams is still dissolved. But If a precipitate starts to form, it's going to continue until you reach the dynamic equilibrium that you had originally, so that 9 grams will come back out. Okay, here's another example, sodium thiosulfate. The solute is added to hot water until the solution is saturated. Then you're going to filter that solution and you drop a small crystal in to seed it. This will continue again until equilibrium is created. Should find a video to actually show you that. But anyway, okay. So all of this is about the idea of what's called solubility. And every solute is going to have its own solubility in a specific amount of solvent at a specified temperature. It's basically explaining using numbers how easily something dissolves in a solvent, usually water. An example of solubility is of sugar. It is 204 grams of sugar per 100 grams of water at 20 degrees Celsius. Again, if you increase the volume, or you increase, I should say increase or decrease the volume of solvent, or if you increase or decrease temperature, this number is going to change, which is why it's specific for the amount of solvent and for the temperature. Okay, so you have to specify temperature. Solubility is generally done per 100 grams of water. And again, it's the same thing as 100 milliliters because of the density of water. Now, gases can also dissolve, but for gases, you also have to specify pressure, because pressure affects the solubility of gas. It does not affect the solubility of solids or liquids. But the rate at which a substance dissolves is unrelated to its solubility. So it's not, solubility is not about how fast it dissolves, it's about how much dissolves. Okay. Now, I've mentioned since like the beginning of time when I started teaching you about this idea of like dissolves like. In general, this is used to describe the solubility between polar and non-polar substances. But it's a bit more complicated than that, because it's not just about whether something is polar or non-polar. It also depends on bonding and intermolecular forces between the solute and the solvent. Dissolving ionic compounds is probably the easiest, because ionic compounds are made of ions and water is a highly polar substance. The polarity of the water is what is able to separate the two ions from each other. Now, when that happens, the solute particles are called hydrated, because as you can see here, they are surrounded by water molecules. So the polarity of the water molecules, you can see here, the negative end of the water molecule, which is the oxygen, is facing the positive sodium ion, and the opposite is true for the chloride ion. It's the positive end of the hydrogen. Did I say ions? I didn't mean that. The positive ends of the hydrogen atoms in the water molecule are what are going to be facing the chloride ion. So this is called hydrated. That's what happens when you dissolve ionic compounds. So the charged ends of the water molecules attract the ions, surround them to keep them separated. Okay, this process is called hydration. The ions, as I said, are called hydrated. As hydrated ions diffuse into solution, other ions are then exposed at the surface and drawn away from the crystal. Okay, it's the same thing as I described when dissolution happens, because this is what happens when an ionic compound dissolves. Now, when a crystallized form, when an ionic compound is crystallized from an aqueous solution, Some ionic compounds are going to form crystals that actually bring some of the water molecules with it. These crystalline compounds are called hydrates, and they're going to have a very specific ratio of water molecules. You will see these crystals represented with formulas such as copper 2 sulfate, and then a small dot, and then 5H2O. This means for every copper sulfate crystal that has been crystallized from an aqueous solution, it's going to come with 5 water molecules. So if you are, for some reason, shopping for chemicals and you need something called anhydrous copper sulfate, you would look for this, and that would be just the copper sulfate. Otherwise, you'll see hydrated. I cannot write anymore. Hydrated copper sulfate, and then a little dot, and then the specific ratio. And so each crystal is going to have its own ratio of water molecules. When a crystalline hydrate dissolves in water, of course, the water from the hydrated crystal is going to return to the solvent. So if you have this and you dissolve it, you're going to have the copper ions, the sulfate ions, and these 5 water will just go back to the solution, which is indicated by the aqueous notation there. Now, it's important to understand that the behavior of a hydrated crystal is no different than the anhydrous form. So they don't act differently just because it's hydrated. What about nonpolar solvents? Nonpolar solvents do not attract the ions of ionic compounds strong enough to overcome the forces holding the crystal together. This is why an ionic compound will not dissolve in oil, because the oil is nonpolar. There's no partial charge there to separate the 2 ions from each other. Now, if you have liquid solutes and liquid solvents, an example is a bottle of Italian dressing, which is usually made with vinegar and oil. Vinegar, again, is acetic acid, which has the formula CH3COOH. This right here makes one end of the vinegar slightly polar. Why didn't it work? Okay. And then when you add oil, they don't mix, okay, because of the OH in the carboxyl group. If you stop shaking your Italian dressing, the strong attraction between the water molecules is going to squeeze out the oil and form separate layers. So we have a word to describe 2 liquids that are not soluble in each other, and that is immiscible. If you have liquids that can dissolve in each other, they are miscible. Okay, this is only used for liquid solutes and solvents, liquid solutes, liquid solvents. Okay, so here's an example of hexane, which has the formula, let's see, hexane, so that's C6, and that's 2n plus 2, so it'd be H, 2n14, 2n plus 2, 2, yeah. Yeah, so hexane C6H14, that is a pure hydrocarbon, which means there is 0 polarity there, because remember, polarity comes from oxygen-hydrogen bond. If you don't have oxygen, you only have carbon and hydrogen, then that is purely nonpolar. So you've got hexane and water, which of course is highly polar, so they form immiscible layers. Nonpolar substances are generally quite soluble in nonpolar liquids. So if you have, say, a degreaser, which you can find in hardware stores. You can find them in the cleaning aisle for like usually around kitchen tile, like for kitchen tiles, around your stove, that kind of thing. They're going to be non-polar liquids that are going to help to break up the fat or the oil or the grease. The reason for this is because they're the only attractive forces in nonpolar molecules are weak London forces. If you don't remember what London forces is, and I will just assume that you forgot, is that when you have an atom with electrons, even for a purely nonpolar atom, the electrons are moving around the nucleus. So at any one time, if you were able to freeze an atom at any point in time, you could have more electrons on one side than you do on the other side, as in the case with these two atoms. So if I freeze these two atoms on this side, I've got 3 electrons, on this side, only 1. So at this particular like femtosecond in time, you have a slightly negative charge on the right-hand side, which makes this side slightly positive. And the same thing for this atom, a slightly positive side, just because relative to the other side of the atom, it doesn't have as many electrons. So for a tiny, tiny, tiny split fraction of a second, you have a slight attraction between these two atoms, just because you've got a slightly positive and slightly negative side for, just like I said, that one really super quick moment in time. Those are called London forces. Okay, London dispersion force, same thing. And I just described that. So here's another example. When you have any, what do you call it? Like any instance where you have opposite charged sides of an atom, we call those dipoles, which obviously just means 2 poles. So these are instantaneous dipoles. For this one, it's called instantaneous because of the movement of electrons around the atom. Now for this one, this is called induced dipole because we're looking at helium, right? Helium has only 2 electrons. So here's the first illustration. In this example, both electrons are on the left-hand side, and this creates an instantaneous dipole, which means like it automatically and instantly creates a negative charge on the left-hand side, a positive charge on the right-hand side, because you have this positive end of this helium atom, it actually attracts the electrons from a second helium atom. And that's why it's called induced dipole, because this dipole caused the neighboring helium atom to become negative on that side, if that makes sense. Okay, so this is just another representation of how dipoles are created. So you've got 3 electrons here. If they're evenly distributed, you have a neutral atom, but in this example, all 3 are on one side. So you create an instantaneous dipole where you have for a short time a negative end and a positive end. This negative end can create a positive end in the next atom. This positive end can create a negative end in the atom next to it. Liquids that do dissolve freely in one another in any ratio, as I explained before, they are called miscible. So 2 examples of nonpolar liquids are benzene and carbon tetrachloride. So carbon tetrachloride, you should remember how to name that, is CCl4. Tetra is 4. It tells you how many chlorine atoms there are. If there's no prefix on carbon, it implies that there is 1. Benzene, I don't remember the formula, the chemical formula for, but it looks like this. And what the circle represents is basically a 6-ring carbon hydrocarbon with 3 double bonds. But because the double bonds, and I'm gonna like really brings back some memories for Lewis structures. This is a resonance structure. because every other bond is a double bond. So the double bonds for this one can occur here, here, and here, or the other three here, here, and here. So you get what's called a resonance structure. If you don't remember what resonance structures are from last year, that's when we draw Lewis structures, but there's no one Lewis structure that can represent the possible positions of electrons. And so you need to use more than one representation. And so in the end, we decided that using the circle would be an indication of the resonance between the two versions of benzene. Anyway, the point is, and I should explain what the structure means. This is a super condensed way to draw structural formulas in organic chemistry. And I apologize because I'm getting ready to teach grade 12 OChem. But what these represent, each corner is a carbon atom. And the line just represents the same thing it always does, as a single bond. And then if there's nothing else in the structural formula, you just assume that the rest of the bonds are made with hydrogen, because it takes, look how long it takes to draw this crap. Yeah, I'm not going to draw the rest of that. So that would be the extended version. But when we condense it, we use line drawings. Whoops. Okay, so these two liquids, bottom line is that they are miscible because they're both nonpolar. They are, there's no strong repulsion or attractive forces, so they mix freely together. On the other side, if you have two polar liquids like ethanol and water, ethanol, C2H, oh gosh, no, I haven't done this in a long time. H, was it 2N plus 2, so that's 6, but I got OH, so that's 5 or 4. I don't know. Don't really remember what number this one is. But anyway, the F means that the carbon is 2, and the ol means that you've got the OH. You'll learn that next year. Anyway, the OH makes ethanol polar. And of course, we all know that water is polar. So they are also completely miscible. Okay. Gasoline is mostly non-polar hydrocarbons, which makes it an excellent solvent for fats, oils, and greases, because the only intermolecular forces, as I said, are the very weak London forces. Ethanol is less polar than water, but it is more polar than carbon tetrachloride. So it is a better solvent for less polar substances because of its non-polar region. There we go. I was right. C2H5. So we've got C2, 1, 2, H1, 2, 3, 4, 5, and then OH. That's the functional group. So as a chemical formula, you write it at the end. Now, I did mention before that pressure affects solubility, but it only affects the solubility of gases, because pressure does not have any effect on liquids or solids. But if you increase pressure, you're going to increase the solubility of the gas. I just try to visualize this in my head and think about like compressing a gas that's on top of a liquid. So you're basically squishing the gas into the liquid, and that's how you can dissolve more. Remembering back from the chapter on gases and the kinetic molecular theory, when a gas is in a contact with the surface of the liquid, the gas molecules can enter the liquid. As the amount of dissolved gas increases, some of the dissolved gas molecules can start to escape. Again, having this equilibrium between gas that is entering the liquid and gas that is leaving. As long as that equilibrium is undisturbed, the solubility of the gas, of course, is unchanged at a given pressure. This is going to have to include pressure, and I should have added temperature, which is also important, because if you increase the temperature of a system at equilibrium between a gas and a liquid, then you're going to increase the amount of gas that will escape into the gas phase. Okay. What I want to do is try to bring this into like why we care, is because when you go to drink your bottle of Coke or whatever, the first thing that you notice as soon as you open, trying to get to my picture here. Sorry, I'll go back. Here we go. So as soon as you open this bottle of Coke, you notice that you hear a ksh, and that is because all of your carbonated beverages are bottled under an increased pressure, usually between 5 and 10 ATM, because you are forcing a high amount of carbon dioxide to dissolve in basically what amounts to sugar water. And I'm sure we've all had flat Coke, which is, in my opinion, disgusting. But that's all it is, because if you let your glass of Coke sit out at normal atmospheric pressure, it doesn't take very long for all of the carbon dioxide to escape, which means that you would never be able to put that much carbon dioxide into the water at atmospheric pressure. So this is something called effervescence. This is what happens when you force a gas to dissolve in something under a high pressure, and then you open the container at a lower pressure. It's a rapid escape of gas. Sometimes, I don't know if you have them here, but what's it called? There is not a medicine, but like, yeah, I guess it was a medicine. Usually for people that are like hungover or have got like an upset stomach or something in the morning, they plop these 2 little kind of chalky tablets inside a glass of water. It's called Alka-Seltzer. And basically it does kind of the same thing. It has all these bubbles released because when they make these tablets, because they're solid, they are dissolving gas in this solid. So then when you add it to water, it's releasing all that gas. So just to go back to Henry's law, Henry's law is just the law that states that increasing pressure is going to increase the solubility of a gas. Again, in my mind, I think it just kind of makes common sense. If you think about increasing pressure, you're going to basically like squish more gas into the liquid. And again, constant temperature, because you change temperature, you're going to change solubility. Okay. Right. So carbonated drinks, they increase the solubility of the carbon dioxide by increasing the pressure when they bottle it. And like I said, they've got flavored water, and then they have, I'm assuming it's like under a vacuum pressure or something like that. They create a pressure between 5 and 10 ATM. So there's much more carbon dioxide that can dissolve. Then they seal the bottle and then it comes out, which is why if you shake the bottle or the can before you open it, you're basically forcing that dissolved gas into the small space that's above the liquid line. And then when you open it, finally, it's going to explode. Okay, so there you see a nice illustration of effervescence, how the bubbles kind of just pop out of the solution. And I've already talked about temperature, so there's no need to go over that again. And what else? Oops. Right. So this is just an example of some solubility curves. It's just showing you in general for all of these different solutes that as you increase temperature, the solubility also increases. The only exception seems to be, I think, the lithium sulfate here, which looks like it decreases slightly. Excuse me. Okay, last thing. Do I have time? 10 o'clock? Yeah. Oh no. Oh shoot. No, 10 o'clock is it. Okay, never mind. I don't want to be too late because